All right, in this section, we're going to cover areas and distances and begin our discussion by looking at the area problem. So one of the common questions or problems that we want to tackle when we're studying calculus is how to find the area underneath a curve. And so for this example, we're going to consider y equals x squared just on the interval from 0 to 1, and say we were interested in finding the shaded area. Well, this is not some fixed geometric shape that we have a formula in order to compute its area. So what we're going to do is approximate the area. And then as we continue our discussion, we're going to look at how we can improve that approximation. Okay, so the process that we're going to use is we're going to make rectangles to estimate the area. So what we're going to do is form several small rectangles, and we know how to find the area of a rectangle, right? It's just length times width or base times height. And by finding the area of the rectangles underneath the curve, then I'm going to have an approximation for that yellow shaded area, okay? Well, to begin, let's just make 4 rectangles, okay, from the interval from 0 to 1. And I'm going to use right endpoints from the curve to determine the height of each rectangle. So look at the second drawing here. It's going to show what's going on in more detail. So we have the interval from 0 to 1, right? And I'm going to create 4 rectangles with equal bases. So the base of each of them is 1/4, 1/4, 1/4, 1/4. Now the height of each rectangle is determined by taking the right endpoint of each interval. So if I'm breaking up the interval from 0 to 1 into 4 subintervals, I'm going to use the values on the right of each subinterval to evaluate the function. So 1/4, 1/2, 3/4, and 1, okay? And so the height of the first rectangle is given here by f of 1/4, so substituting in 1/4 for x into x squared. The height of the second rectangle is determined by taking 1/2 and plugging it into our function. The third rectangle's height is determined by taking 3/4 and plugging it into our function. And the last one is by taking 1, the endpoint of the interval, and substituting it into our function. All right, could we compute the area of each of these 4 rectangles? Sure. So we have base times height. So the area for the first rectangle is going to be its base, which is 1/4, times its height. Well, the height of the first rectangle is going to be 1/4 squared, right? I'm substituting that into y equals x squared, and the x value at the right endpoint of the first subinterval is 1/4. So this is going to give us 1/64. The second rectangle's area, so this is a 1, this is a 2. Again, its base is 1/4, all right? Its height is going to be 1/2 squared, so that's going to be 1/4 times 1/4, which is 1/16. The third rectangle, a 3, is going to be 1/4 times 3/4 squared. So this is 9/64. And the last rectangle's area is 1/4, that's its base, times 1 squared, which is 1/4. And here's a 4. Okay, so let me highlight. Here's a 4, a 2, a 3, excuse me, a 2, and a 1. All right, so we say R sub 4, meaning the sum of these 4 rectangles that were made using right endpoints to determine their height is equal to A1 plus A2 plus A3 plus A4, and this comes out to 15/32. So notice something important here. So the subscript tells you how many rectangles or how many subintervals were used to create the approximation, and R tells us that we used right endpoints for each of those subintervals to evaluate the height of the rectangle. Now let's look at the approximation that we have R for versus the true shaded area. Well, notice each of these rectangles lies above the curve y equals x squared. So that means it's an overestimate of the true area. So we can say that the shaded region is less than R4, right? So we know clearly it's not equal, the exact area under the curve is not equal to 15 over 32. It's going to be some value less than that. Okay, well, what if instead of using right endpoints, we formed 4 rectangles, but this time we took left endpoints to determine the height of each of the rectangles. So here, let's go back and label in. This would be A1, my first rectangle, A2, A3, and this one right here is A4. Okay, so the base of each of them is still 1/4. So A1's area would be 1/4 times, now the left endpoint on the interval from 0 to 1/4 is the x value of 0. So I would substitute 0 into my function, and the first rectangle has an area of 0, right? You can see there's no height to it. Now the second rectangle's height is determined by taking that left endpoint of 1/4. So I would have the base of 1/4 times 1/4 squared, right? Because my function is y equals x squared. And this is going to be 1 over 64. All right, A3 is right here. So base is still 1/4. Height is going to be 1/2 squared, right? See the left endpoint here. So this is going to be 1/4 times 1/4, which is 1/16. And then A4, base is still 1/4. The height is going to be determined by taking 3/4, substituting it into the function. So I have 1/4 times 3/4 squared, which is 9 over 64. Okay, so now we call this the sum of these 4 rectangles L4, L standing for the fact that we use left endpoints from each subinterval to determine the height of the rectangles, and 4 because there were 4 rectangles. And this comes out to 7 over 32. Now let's look at our approximation versus the true area. So here's A4, A3, A2, and A1 had no area. So would you say that L4, in comparison with our original curve, does a good job? Well, we don't know that, but I do know that it's an underestimate, right? The true area under the curve is greater than 7 over 32. So now I can bound the true area underneath the curve. I can say that the true area, our last estimate, R4, was an overestimate. So the true area is less than R4, and it's also greater than L4. So it's something in between 7 over 32 and 15 over 32. But that's still causing quite a bit of room for error, right? So how could we improve our approximation? Well, what we would do is just create more rectangles, right? Why are we only making 4? Why not make 8 or 16 or so on and so forth? Then we would have less of an overestimate or underestimate by creating more and more rectangles. And that's the idea that we're going to build upon in the rest of the lesson. And later on, we're going to show that the area underneath the curve is actually closer to 0.33 or 1/3. Okay, so let's practice using rectangles to estimate areas under curves for now, and then we're going to work on improving our estimate. So first we're going to consider a new function. Instead of y equals x squared, let's move on. And we're going to estimate the area underneath the graph of f of x equals cosine x from x equals 0 to pi over 2 using 4 rectangles. And for the first part, we're going to use right endpoints. For the second part, we're going to use left endpoints and then determine which one's an underestimate, which one's an overestimate. So to begin, we have to draw a picture. So for part A, we're going to be using right endpoints. Cosine of x from x equals 0 to pi over 2. Well, we know at 0, cosine is equal to 1. And then we're only going up to pi over 2. Here's my x-axis. And we're using 4 rectangles, right? 4 rectangles. So here's how you want to think of it. If your interval is from 0 to pi over 2, then each of the bases is going to equal pi over 2 divided by 4. right? Which would be pi over 8. So that would be the length of each of the subintervals. So here I'm going to cut it in half, that's at pi over 4. Cut it in half again, that's pi over 8. And then cut it in half one more time, that's 3 pi over 8. Okay? And you don't have to draw a super perfect graph, just know that cosine x is 1 when x is 0, and then it's 0 at pi halves, and it curves downwards, right? It's concave down. Okay, so for right endpoint estimate, I would use, for the interval from 0 to pi eighths, that would be my first rectangle. That's A1. For my second rectangle, I would use pi over 4. For my third rectangle, I would use 3 pi over 8. That's A3. And for the fourth rectangle, I would use pi over 2. So you can't even see it. Ooh. Okay, so let's list it out. So R4 is going to equal, now notice the base on each of these is pi over 8. It's equal, right? So I can just take pi over 8 and then multiply by the function heights at each of those 4 endpoints, the right endpoints. So pi over 8, pi over 4, 3 pi over 8, and pi over 2. So I have pi over 8 times cosine of pi over 8 plus cosine of pi over 4 plus cosine of 3 pi over 8 plus cosine of pi over 2. All right, and then you could substitute all these in your calculator, and we end up with approximately 0.7908 for R4. All right, now would you say this is an overestimate or an underestimate? Always use the graph to determine, okay? So notice each of these rectangles lies below the curve. So in this case, R4 is an underestimate. Now in the previous example with y equals x squared, R4 was an overestimate. So why is it different in this case? Well, it depends on the concavity of the curve that you're dealing with. Y equals x squared is concave up, and in this case, cosine of x is concave down on the interval from 0 to pi over 2. So don't memorize, but just use the graph to help you determine whether or not your approximation is an overestimate or an underestimate. All right, now let's perform the same estimation, but this time we're going to use left endpoints. So we're going to divide up the interval in the same way. So from 0 to pi over 2, here's 1, here's pi over 2, here's pi over 4, pi over 8, 3 pi over 8. Cosine starts at 1, goes to 0 at pi over 2, and this time I'm taking left endpoints. So I'm going to use 0 for the height of the first rectangle. That's A1. I would use pi over 4 for the height, pi over 8, excuse me, for the height of the second rectangle. Then pi over 4. And then 3 pi over 8. Okay, good. So L4 is equal to pi over 8, and then I would have cosine of 0 plus cosine of pi over 8 plus cosine of pi over 4 plus cosine of 3 pi over 8. And L4 comes out to approximately 1.1835. All right, would you say this is an overestimate or an underestimate? Remember, use the graph and look at these rectangles. And you see how the height of each of them is a little bit above our curve cosine x? Well, that means then that it is an overestimate. Okay, good. So, like we said before, this taking a finite number of rectangles here gives us an approximation, but it's not an exact value for the area underneath the curve. And we're not happy about that. So what we want to do is improve our estimate. And now that we're in calculus, we can talk about things like infinitely many rectangles. So what I want to do is find a formula for the area under the curve using n number of rectangles. So I'm going to leave n as a variable. And then what we're going to do is take the limit as n goes to infinity, because the more and more rectangles we use, the error starts approaching 0. And so we want to just let n go off into infinity so that we have no error left. Okay, so we're going to go back to our example of y equals x squared, because that function is really nice to work with. And if I had n many rectangles, the width or the base of each of them would be 1 minus 0 divided by n. Well, where does that come from? Well, it was just considering the area underneath the curve on the interval from 0 to 1, right? And last time when we had 4 rectangles, we took the length of that interval, which is 1 minus 0, and we divided by the number of rectangles, which was 4, and that's how we got the base of 1/4. Well, this time we're saying we want to leave n as a variable, n many rectangles, so the base of each of them would be 1 over n. Okay, and then the height in this particular case, using right endpoints, would be 1 over n squared. If you zoom in here, or I'll just draw the x-axis out separately, how about that? So here's your interval from 0 to 1, right? So the base of each of them is 1 over n. So that's 1 over n, add another 1 over n, now it's 2 over n, add another 1 over n, it's 3 over n, etc. Right? And if we're using right endpoints, then I'm going to evaluate the function here. So you would have f of 1 over n, f of 2 over n, f of 3 over n. This is because we're taking right endpoints. And then your last one would just be f of 1. And our function here is x squared, which is why the height of each rectangle comes out to be 1 over n squared, 2 over n squared, so on and so forth. So my right endpoint approximation for n many rectangles is going to be 1 over n. This is the base, right, or the width. That's the width. Times the height, which is the function value, starting at 1 over n, all the way up until n over n. That's the last one. And then notice each of these has the same base of 1 over n, or the same width, so I can factor that outside of the expression, just like we did in the previous example, how we factored out that pi over 8 for cosine. Okay, then all I'm left with is 1 over n squared, 2 squared over n squared, 3 squared over n squared, the sum of all those terms. Notice again, they all have n squared in common in the denominator, so I can factor that out as well. And then I'm just left with 1 over n times 1 over n squared times the sum 1 plus 2 squared plus 3 squared plus ... up until n squared. So we have 1 over n cubed sitting outside, and then we're going to study this more in the next section, but the sum 1 plus 2 squared plus 3 squared plus up until n squared we can replace with the following expression. Okay, that's more to come in section 5.2. And then simplifying from here, I can cancel out one of the n's here so that I just have n squared. So now we have 6n squared in the denominator, and then n plus 1 times 2n plus 1. All right, so remember we said that as the number of rectangles increased, our error went to 0. And so we want to take the limit as n approaches infinity of r sub n, and this would equal the limit as n approaches infinity of 2n squared, I'm just going to multiply out the numerator, plus 3n plus 1 over 6n squared. And then when I take this infinite limit, degree of the numerator equals the degree of the denominator, so I can just divide the leading coefficients, and this is 1/3. Okay, so we have the limit as n approaches infinity of r sub n is 1/3. And similarly, we can show that the limit as n approaches infinity of L sub n using left endpoints is also equal to 1/3. Ooh, very exciting. So therefore, we can say that the exact area underneath the curve y equals x squared on the interval from 0 to 1 is equal to 1/3. So notice I don't have any approximate, there's no error here, we know that it's exactly equal to 1/3. And notice that my right endpoint and left endpoint approximations are exactly equal to each other because they're not approximations anymore. They represent the exact area under the curve. So it doesn't matter if you use right endpoints or left endpoints as long as you take infinitely many rectangles and your function is integrable. Okay, so this is exciting news for us. We love having no error, right? So here's our definition. The area under the graph of a continuous function f of x, so the function has to be continuous, is equal to the limit as n approaches infinity of r sub n. Remember, that's the approximation used taking right endpoints, which is the limit as n approaches infinity of delta x times f of x1 plus delta x times f of x2 all the way up until delta x times f of xn. So delta x you could think of as your base. So that is the base of each rectangle, or the width. Okay, and if we're finding the area underneath the curve of a function on the interval from a to b, then in order to find delta x, you would take b minus a, the length of the interval, and then divide it by n. And then f of x1, f of x2, all the way up to f of xn, that's the function being evaluated at the right endpoints. Now notice the difference here. If we're talking about left endpoints, my first function evaluation is at f of x0, and the last one is at f of x sub n minus 1, right? Because we take left endpoints. Versus right endpoints, you start at x1. Also, who's to stop us to only use left and right endpoints? We can use any function value on each of those subintervals, and that's why sometimes you'll see a star represented if it's not necessarily left or right. So f of x1 star, x2 star, up until xn star. Sometimes you use the midpoint, or sometimes you might take some other value to evaluate the function. So x sub I star is any number on the ith interval. Notice these all give you the exact area underneath the curve once you take that limit as n approaches infinity. And as long as your function is continuous, it means it's going to be integrable, and so all of these limits will have the same value. All right, now using sigma notation, right, who wants to write out this sum over and over and over? I can just replace it and write the limit as n approaches infinity, so that stays the same. And then we have the sum, I equals 1 to n, of delta x times f of x sub I. That's for right endpoints. The next one is for left endpoints, and the last one is for some arbitrary partition. So the one we're going to work with in this class is the right endpoint version of the formula. Just because it's the nicest to work with, since we just start from 1 and go up until n, and we know that they all come out to be the same. So there's no need to work with all three formulas necessarily at this point in your calculus career. Okay, good. So find an expression for the area under the graph of f as a limit. So basically we just want to use this definition and expression in sigma notation to find an expression for the area underneath the graph of the following function. So to build it, we need to start with the following. So we need our delta x, right? The base of each of them. So delta x is equal to b minus a over n. In this case, there's a, there's b, so this is going to be 10 minus 3 over n, which is 7 over n. All right, looks good. Now, the next part of the formula involves f of x sub I. Well, what's x sub I? All right, let's draw out our interval here. Okay, and it's from 3 up until 10, right? So each delta x is going to be the base of the rectangle, so on and so forth. So this is a delta x, this is a delta x, this is a delta x. And remember, we're using right endpoints to evaluate our function. So that would mean on this first subinterval, I would take the height of the rectangle by plugging in whatever value for x that is. Well, what is that? That's 3 plus delta x, right? That's x1. What about this next one here for my second rectangle? That's x2. Well, x2 would equal 3 plus 2 delta x's. And if I wanted an expression for x sub I, right, my ith subinterval, then that would be 3 plus I times delta x. Okay, so if you want an arbitrary formula for x sub I, general formula, x sub I would be a, right, whatever the start of your interval is. In this case, we started at 3 plus I times delta x. So in our case, it's 3 plus I times, there's delta x, 7 over n. And then we can just clean that up and write it as 3 plus 7i over n. So this is always the order that you want to do it in. You want to find delta x first, x sub I next, and then lastly, f of x sub I. So I'm going to substitute 3 plus 7i over n into the function. So this is going to be 3 plus 7i over n squared plus radical 1 plus 2 times 3 plus 7i over n. Okay, so now we're going to put everything together. So the exact area underneath the curve equals the limit as n approaches infinity. Remember, that makes our error go to 0. I'm adding up all the rectangles. I start at I equals 1, I end at n. I have the base of each rectangle. Base is 7 over n, or the width, times the height, the function value, which is going to be 3 plus 7i over n squared plus radical. And then we will clean this up a little bit. That's 6. 6 plus 1 is 7 plus 14i over n. Oh, what happened to this guy? Okay, this is an n. And that's our final answer. We're not going to evaluate this limit. Don't worry, that's for the next lesson. But when you're building this, I want you to think of it this way. This is the base, or the width. This is the height for each rectangle. Here, we add them all up. And then this makes our error go to 0. And if you think of it that way, then the formula won't seem so arbitrary. All right, so that concludes the lesson. Hope you enjoyed it, and then stay tuned for the next video because we're going to actually evaluate this limit for various kinds of functions.